So when we talk about how much thermal energy a substance has, that is a question that involves the temperature of that substance. So there are three temperature scales, two of which you are probably already familiar with. The one that we Americans use when talking about the weather, recording temperatures here, is in the Fahrenheit scale. Celsius is the scale that is used in Europe, across the pond, to measure temperatures. The standard international unit of temperature, the one that scientists use when talking about temperature, is the Kelvin scale. Each of these have unique histories behind them as to why the scales are the way they are. What you need to know is that there are three temperature scales. They are related to each other. When we do calculations in chemistry, we are primarily going to be using temperatures that are in the Celsius scale or that are in the Kelvin scale. And Kelvin scale is going to really be important when we start talking about doing calculations regarding gas laws in Unit 4. Kelvin is the only temperature scale that is based upon a zero where there is no molecular motion, where all motion ceases. And that is going to be important again when we talk about gases. But what you just need to know now is that there are three temperature scales, Fahrenheit, Celsius, and Kelvin. We will be using primarily Celsius and Kelvin in this class. And those three temperature scales are related to each other. And so you should feel comfortable being able to convert between one scale and another using these three equations. And you will note that when going to Kelvin, when converting to Kelvin, you have to go through the temperature in Celsius. There is no direct conversion unit to go from Fahrenheit to Kelvin. But that's okay, because if I have a temperature that's in Fahrenheit, if I have a temperature that's in Fahrenheit, I can use this second equation down here to convert it into Celsius and then go on to convert it into Kelvin, which is what we're going to do in this next example. And I chose this example, gosh, several years ago because it was right after my trip to Yellowstone, which is a wonderfully beautiful place. It's open back up now, so if you have a chance, I would really recommend. It's quite a drive, but I would really recommend going. It's gorgeous. But someone was not very smart when he went to Yellowstone and decided to check the temperature to take a bath, and he lost his life, unfortunately. According to the article that was associated with this headline, scientists measured the highest temperature in the park at this particular spring at 459 degrees. Now, there were a few things that really irritated me about this article, not the least being that someone was foolish enough to try to get close enough to a hot spring at Yellowstone. But as a scientist, this article irritated me because when they reported the temperature, 459 degrees, they didn't tell me the scale. I don't know if it was Celsius, Fahrenheit, or Kelvin, but I'm pretty sure based upon what that number is that they were reporting this in Fahrenheit, but they should always have reported the unit associated with the measurement, just like you guys should do when doing problems in lecture and lab. But let's say I wanted to take this 459 degrees Fahrenheit, and then I wanted to know what that temperature is in Celsius and in Kelvin. So to do that, I would make use of the conversion equation that goes from Fahrenheit to Celsius. So I would put in my given and do that subtraction and division. And on these conversions, I'm not going to be as picky on sig figs as I was in Chapter 2. Technically, this number should have a total of 3 significant figures because the 32 and the 1.8 are exact numbers. You can think about it as like exactly 32, exactly 1.8. And so my temperature would be based upon what's given, which is the 459. So when doing that subtraction and division, I get a Celsius temperature of 237 degrees. So that is that is 459 degrees Fahrenheit in Celsius. And then if I wanted to go and convert that to Kelvin, I would add 273.15 to that to give me 510 Kelvin. So you should feel comfortable going between Celsius, Fahrenheit, Kelvin, and vice versa. You should feel comfortable in being able to convert temperatures from one scale to another. Let's talk a little bit about the units of heat energy. So temperature is a measure of thermal energy for a system. We said that the variable Q is the heat energy that's associated with a piece of matter. Obviously, temperature is going to come into play when calculating how much heat energy something has. But what units do we use to report heat energy? Well, the units for reporting heat energy, these are the most common ones. You've probably heard, I'm sure you've heard of calories. This capital calorie is what is thought of as the nutritional calorie, or the kcal. But the standard international unit, the unit that we chemists or that you're going to use in this course for chemistry when doing calculations with regard to heat energy, that standard international unit is the unit of joule. Capital J is the abbreviation. So you do not need to memorize these. You'll obviously be able to use them for quizzes and exams, but you should be able to convert a unit of heat energy from joules to a particular unit based upon these conversion factors. So let's do an example from one of my favorite Texas restaurants, the Big Texan, which I hope is open now. I don't know if they're still closed or not. But I admittedly have not tried the 72-ounce steak challenge meal. I have watched people try and not be successful at trying to eat that meal. If you don't know what I'm talking about, go ahead and Google Big Texan 72-ounce steak, and you'll see all of the food that you have to eat in their Big Texan meal within 1 hour for you to get it for free. But it's a lot of food. It's so much food. It is approximately, according to their website, 6,937 calories. That's including the baked potato, the salad, the bread. I think there's a dessert too in there. But let's say we wanted to try it, and I wanted to know how many joules of energy are in that many calories, and I wanted to know how many kcals that was. Well, that is a units conversion question, and so you can use your unit conversion or dimensional analysis skills from Chapter 2 to solve this problem. You can use those skills in combination with these conversion factors to solve this problem. So I'm going to solve it by write down what I'm given. I'm looking for joules, and so I see that for every 4.184 joules, there's 1 calorie. And so I write that equivalency as a conversion factor or as a ratio so that my calorie units cancel, and I'm left with joules in the numerators because that's the unit I'm looking for. And so multiplying these two numbers together and reporting my answer in scientific notation to 4 sig figs should give you 2.902 times 10 to the 4th joules. So that's how many joules of energy in that meal. We wanted to figure out how many kcals that would be. We would use this conversion factor that for every 1 kcal there's 1,000 calories. Again, written so that my calorie units cancel, and I'm left with the unit I'm looking for in the numerator. And so doing that division, remembering that all numbers that are in the denominator are divided, should give you an answer of 6.937 kcals. So that's sort of an introduction to temperature conversion, units for energy, for heat energy and heat energy conversion. In the next video, we're going to take temperature and heat energy and put them together to find an equation that's used to actually calculate the amount of heat energy a substance has based upon its mass, its temperature, and something called its specific heat.